All right, so we are looking at MCMC, and we're applying it to deciphering some text, okay? And I guess effectively what we're trying to figure out is the probability of a letter mapping given our text, okay? So our data is the text. We're trying to figure out the probability of a certain letter mapping, and ideally we want to find the letter mapping that has the highest probability, okay? And what we know is that this thing is going to be proportional to the probability of the text given our letter mapping multiplied by the prior probability of letter mappings, okay? And we're going to treat the prior probability of letter mapping as just uniform. We're going to say all 26 factorial permutations are equally likely. So really, if that's the case, then this value is going to be the same for all possible letter mappings. And so we can just say the probability of a letter mapping given our text is going to be proportional to the probability of our text given our letter mapping, right? And we said the probability of our text given the letter mapping, at least according to our model, okay, so this is our letter mapping model, letter mapping text model, is that this is going to be a combination of, we look at the words that appear, okay? So it's going to be the product of the probability of each word that appears in the text given a particular letter mapping times the product of the probability of each two-letter combination in the text given our letter mapping, okay? And we said when we do this on the computer, instead of dealing with the products because they become really small, we're going to take the logs so that we get negative numbers and do that. Yes, question? Oh, yeah, there's supposed to be a closed parentheses. Yes, of course. Okay, so instead of dealing with a product, because, well, this is, how the text works, right? So, yeah, I mean, this is a simple word probability model. In real life, the word probabilities are more complex, right? Because here we're just doing probabilities of each word that appears in the text, whereas in real life, we could look at like n-gram probabilities, n-grams being things like when you see the word going, what's the likely word that follows going? 2, right? And so that would assign a higher probability, okay? So if we see the word going, 2, that would return a higher probability than like going, going, I don't know, desk or something like that, right? That's less likely, okay? We're not even considering that. This is a simple model that just says, you know what, let's look at the probability of going, let's look at the probability of apple, let's look at the probability of desk, 2, and all of that, and we're going to just multiply those two together, okay? And we're also, because we're in a kind of a deciphering context, where a lot of the times we're not going to have complete words in the beginning, we're just going to look at also two-letter probability transitions, okay? And of course, we can make things more complicated and look at like three-letter transition probabilities, but those get much, much more complicated, right? Because, for two letters, we've got 27 by 27, 26 letters in a space, 26 letters in a space. So that's, 27 squared. And if we were to go to three letters, then it'd become 27 cubed, and it just grows geometrically that way. So anyway, this is a simple model, but, if you are Google and you're working on text predict for your keyboard, obviously they have more complex models, right? The next word that they predict is based on probably the previous 2 or 3 or 4 words, okay? So you say like, and that's why, you can just keep hitting the middle prediction button and it forms like semi-coherent thought. It's gibberish, but it's semi-coherent also. And but this is just a simple model, and that's what we're doing. Okay, and so I have coded this up I shouldn't say I coded this up. There, different people around the internet have coded it, and I've kind of clobbered certain things together and made something that works for our class. And I'll kind of walk us through the code, and we'll take a look at that. Is that all right? Okay. And on Wednesday we kind of talked about each of these things, right? So I don't have to go further into it. Well, maybe one thing I will say. Okay, so the reason why the Metropolis algorithm works, okay. Okay, so first of all, our proposal distribution is we have a current mapping, okay, which says, A through Z gets mapped to, some letters, okay? Okay, and basically with our proposal distribution is we select 2 letters and we swap them. And so it's the probability of going from, one mapping is equal to the probability of going back to the other mapping, because the probability of taking 2 random letters and swapping them and then swapping them back, it's the same, okay? It would be 26 times 25. 1 over 26 times 25, whatever that is. 1 over 660, 50? I don't know. Okay. 26 times 25, yeah, 1 over 650, I think. Every 2-letter combination, you're just going to take them and swap them, okay? And then, and keep in mind, most mappings are garbage. Okay, meaning the resulting probability is very small. Okay. But some mappings are going to be less garbage than others. Okay, so most mappings are garbage. Some mappings are less garbage. Okay, in that a mapping that makes like if you keep seeing the transition xj, k, or whatever, xj in your text, that's going to be worse than a transition that at least does like bo, okay? Because bo appears like it could actually show up in a word, whereas xj is very unlikely to show up in a word. Okay, so some mappings are less garbage, and the Metropolis algorithm moves towards areas of higher probability, so it will favor these less garbage mappings. Okay, So the Metropolis algorithm favors areas of higher probability, and eventually we will get to an area of decent probability. Quote, high probability zone. Okay, now keep in mind the Metropolis algorithm is not intended to optimize a function. It's just intended to draw a sample from some target distribution space, okay? And technically, there's only one true mapping, but there's other mappings that have non-zero decent probabilities. And so the Metropolis algorithm will sample from these other good mappings, just with less frequency than the quote the one true mapping that should have the highest probability. All right, that's kind of what we're doing. All right, let's just go ahead and take a look at the code, and I'll try to walk us through it, and we'll take a look. Oh dear. Please don't do this to me, computer. Okay, hang on. All right, let's try this again. All right, so we got to give credit where credit is due, and so one place I took some code from this man's website. Okay, really worried now because my computer is freezing up. All right, I'm going to go ahead and close our poll. Sorry. And exit, because I think this is eating, all right, okay. I'm not sure why my computer's not. All right, hang on. All right, I think I'm gonna reboot my machine, okay? Something